Hello friends, in today's class we are going to study the most important topic of your semiconductor physics, that is Hall effect. It is important with respect to diagram perspective, derivation perspective as well as numericals perspective. Hall effect. Well, let's first take a look on what the concept of Hall effect is. It says if a metal or a semiconductor carrying current I is placed in a transverse magnetic field B, well, transverse means perpendicular, a potential difference which is VH is produced in the direction normal to both magnetic field and the current directions. This is known as Hall effect. Well, to put it up, it is as simple as this diagram. Now, as you can see, this gray area is a metallic conductor and I have plugged in a battery, and you can see these are the red color electrons. Now if you see clearly, the electrons are flowing from the negative terminal to the positive terminal. It means I am just talking about the flow of carriers, which are electrons in terms of metal. Now as you can see, all the electrons are going in same alignment. If I place a magnet over it, you can see there is a change in the direction, or there is a deviation in the path of the electrons. You can see the electrons are shifted on the lateral side of the conductor. Hall effects helps us to determine the following: the type of the semiconductor, the sign of the majority charge carriers, the majority charge carrier concentration, the mobility of the majority charge carriers, and the mean drift velocity of the majority charge carriers. Well, the majority charge carriers for extrinsic semiconductor N type would of course be the electrons, for P type it would be the holes, and of course for metals it will be the electrons. So basically Hall effect is applicable on all the semiconductors and of course on the conductors, which are metals. Now let's dive deeper into it. This is a metallic conductor which we have assumed. We have now assumed this to be a p-type semiconductor. Well, why we chose p-type semiconductor? Well, because it has majority carriers as holes, which are demonstrated as positive charge carriers. You can do the same derivation by using n-type semiconductor, and of course then replacing your holes as the majority carriers from electrons to the majority carriers. Now this is the x-axis, this is the y-axis, and this is the z-axis. We'll label them as x, y, and z. This is the current I which is flowing across the conductor. This is the direction of the magnetic field B. Now you can clearly see it is flowing from inside to outside, so it means there's a north pole somewhere at the back and south pole somewhere at the front. This is the direction of the magnetic field. Always make sure you need to understand this point, that magnetic field always originates from the north pole and terminates at the south pole. This is the width, which I am denoting as W of the conductor. This is the height, that's denoted as D, and this is the voltage, which is VH. This is the voltage which I am going to measure, and I am going to name this as Hall voltage. Now we know that I is equals to P into E into A into VD. Well, where this equation comes from? This equation comes from the previous class, wherein we have computed the current equation for a majority carrier. In this case, since it is a p-type semiconductor, we are using P as denotation for the majority carriers. E is the charge of the hole, of course, A is the area, and VD is the average drift velocity. Now, so if I take I on the left hand side, I'll get I by A, which equals to PEVD. Therefore, I by A now becomes equal to J, which is equal to P into E into VD. We all know that J is nothing but as current density. So current density is equals to P into E into VD, and therefore I can define VD as J upon PE. Now let's take a step further. We know that the Lorentz force or the magnetic force will be given as E into VD into B. Now Where this force comes into picture? Well, if you can see, magnetic field acts along the y direction, current flows along the x direction, and if you follow Fleming's left hand rule, then of course you'll be knowing that there's a force which acts perpendicular to the magnetic field. There's a force which acts perpendicular to the magnetic field as well as current, and that force is called as Lorentz force. And as we know from the previous classes, this force is given by the Fleming's left hand rule. Well, the value of the force will be E into Vd into B, where E is the charge, of course, of the majority carrier, that is in case of holes. Vd is the average drift velocity, and B is the magnetic field intensity. Similarly, the transverse electric field force. Now, what is this transverse electric field force? Now, if you remember the previous slides, there was a shift in the position of the electrons. The electrons which were initially going from here to here, and they were continuously going. Now they had a deviated path. The electrons were here, which creates electron density here, and of course the negative charge here, and holes here, which of course is the positive charge. This is what it is called as the transverse electric field. Well, another point to remember, this is the electric field which is transverse or perpendicular to the actual electric field. Well, actual electric field is not shown here, but it is represented as current I. The direction of current will be the direction of the electric field. So an electric field which is perpendicular to the I is nothing but as transverse electric field, and the value of that will be given as E into EH, where I am representing the electric field due to the migration of the electrons as EH. Now, to put on simple words, I'll be using this. Let's say suppose electrons were here, and this is the electric field which led the electron to move in the straight direction. But because there's a magnet present on the top, the electrons will now be located here as well. So this field will be called as the transverse field, and I'm replacing that as EH, which means the Hall electric field. Now, at equilibrium, of course, both of the fields will be equal, and hence I can say that FL is equals to Fe. The force of the electric will be equal to the force of the Lorentz. Therefore, EVB will be equal to E into H. Cancelling E from both the sides, I'll get EH is equals to Vd times B. This is the value for the Hall field. But we know that EH is equals to V by W. Basically, this comes from the equation that electric field is always equal to the potential divided by the distance. So we can replace VH by W in the formula where I'm using EH, and hence here I can replace EH by VH by W and VD as J by PE. Therefore, my equation for VH becomes VH is equals to JBW by PE. Of course, taking W on the right hand side. This is the value of VH, or the Hall voltage. Now, VH is also given by, in the above equation, I have replaced J with its original form, that is I by A. If I convert that, I'll get I by A times BW upon PE. Now replacing A as W into D, of course my W and W gets cancelled, and I'll be getting value of our VH as IB upon PED. So basically we can say my VH holds two formula. One is this and the other one is this. Now, when to use which formula? It depends on the given conditions in the equation. We have to use sometimes this equation 1 and sometimes this equation 2. So now you have the formula for Hall voltage. Let's take a step further. Vd is also called as average drift velocity. If you want to compute its value, you can just use this equation EH by B, replace the value of EH as VH by W, and this equation becomes VH by W into B. Now let's talk about Hall coefficient. Well, Hall coefficient, which is denoted as RH, is defined as Hall field per unit current density per unit magnetic induction. So basically it is a mathematical quantity that is defined as the Hall field, that is EH, per unit current density per unit magnetic induction. Current density JB and magnetic induction is just B. So we can say that RH is equals to EH upon JB. For EH, I'll be replacing with VH by W. Well, why I'm doing so? Because in most of the cases, I'll be supplied with the Hall voltage, and that's why it is important to use VH at all the places where EH is coming into picture. So I've replaced EH as VH by W, hence the equation becomes VH upon JB W. Now, VH can also be represented with the first formula that we talked about in terms of current density, that's JBW upon PE. If I do this, of course JBW gets cancelled and I'll be left with 1 upon PE. As you can see, this is the value for Hall coefficient. Now, let's talk about Hall mobility. Mobility is defined as the drift velocity acquired in unit electric field. It's very important. You should remember this is drift velocity acquired in unit electric field. It means we are taking the value of electric field as 1, and in that electric field, what is the velocity that has been acquired by the charge carriers? So we define this as, we all know that J is equals to PEVD. Of course, this comes from the previous slide, and J is also given by sigma into E, where sigma is the conductivity and E is the electric field. If you equate both of these equations, you'll get PEVD is equals to sigma into E, or you can say VD by E, that is drift velocity acquired unit electric field, is nothing but as sigma upon PE. Now you all know that 1 upon PE is nothing but as RH, therefore you'll replace this as sigma into RH. So you can say your Hall mobility is nothing but as sigma times RH. This has been the most important question for your university exams, which comes for 2 marks. Let's study the next topic, that is Hall angle. The net electric field in the semiconductor is vector sum of electric field along the x direction and Hall electric field. So basically this is electric field along the x direction, which means it's E, and the Hall electric field, that is EH. Now we all know that the net electric field in a semiconductor is nothing but as the sum of the electric field which we have provided and of course the Hall electric field which is attained. So we can say if this is the x direction and this is the net electric field, which is the resultant of the field along the x direction and the Hall electric field, this is E net, and this is the angle theta h. So basically theta h is the angle which E net makes with the x axis. So we can say that tan theta h is nothing but as EH by E. But we know that EH is equals to VH by W, which is equals to BJ upon PE. And we all know that 1 upon PE can be replaced with RH. And of course, E is equals to J upon sigma, which is nothing but as rho into J, because we all know that 1 upon sigma is nothing but as rho. So if you replace this value, you'll get EH by E as B upon PE rho, which becomes B into RH upon rho, because we have replaced 1 upon PE with RH. Therefore, we can write theta is equals to tan inverse BRH by rho. Now, if you know, we can also replace this rho as sigma, and hence the formula becomes equals to tan inverse BRH up into sigma. Let's talk about the variation of Hall coefficient with temperature. Now, first let's talk about metals. In metals, it was found that Hall coefficient does not depend on the temperature. Hence, it may be concluded that concentration of free electrons does not vary with temperature in metals. Well, basically there is a cause and effect for this. Initially, it was not assumed that the concentration of electrons do vary with temperature in metals or not. However, it was proved by the help of Hall coefficient. Since the value of the Hall coefficient did not show any significant change with respect to temperature, it was concluded that the concentration of free electrons does not vary with temperature in metals. Well, but an important point for Viva this could be, if in metals temperature does not play a significant role in increasing or decreasing the carrier concentration, does it affect the resistance? Well, the answer is yes. If you increase or decrease the temperature in metals, there is no change in the carrier concentration. But however, if you increase the temperature, of course the resistance increases. This resistance increases because electrons takes more time for collision and then reaching to the lower potential. Now, coming to semiconductors, the Hall coefficient decreased sharply with increase in temperature. Well, if this decreases sharply with the temperature, it could be found that the concentration of the charge carriers in semiconductors increase with the increase in temperature. Now, let's see where are the applications where Hall effect can be used and what are the outcomes. You can use it to determine the semiconductor type, whether it would be of N type. You can also use for the determination of the carrier concentration, that is if you want to find the value of N and P. You can use for the determination of carrier mobility, that is mu H or mu E. It can be found for magnetic field as well, that is B. In the next class, we'll be doing numericals on Hall effect. For each and every application, we have different numericals, so stay tuned with us. Thank you.